here is the question that I asked at the end of the previous part of this video lecture. And you need to realize here that although I've asked for the velocity at 1 second, because the velocity is clearly constant, because we have a straight line on the x versus t graph, the velocity at 1 second, or at any time, is the same as the average velocity. And so we can find the x component of the velocity just from a rise over run pulled off of the graph. So this rise over run gives me -2 meters divided by 1 second, and so the answer is B. A very common mistake that students make is that they will notice that x is 3 meters at t equals 1, and so they'll take 3 meters divided by 1 second and come up with a Vx of 3 meters per second. But that can't be right. Notice that x is decreasing, so the x component of velocity must be negative. This is why I am careful about my notation and to specify that the average velocity x component is delta x divided by delta t, and that is not the same thing as x divided by t. And you should be careful about this notation as well. Now, before we go any further, there's a misconception you may have just developed that I want to head off at the pass. And as I do it, it's going to become clearer why I've been so careful to define certain quantities in certain ways. So you may now be saying, oh good, so the velocity was positive when the cart was going right, and the velocity was negative when it was going left. And it was going in the positive direction in that early time interval and the negative direction in that later time interval. And I'm here to tell you that's wrong. So I want you to remember, it's very important to remember that there is no such direction as negative. And while I'm at it, I'll point out there's also no such direction as positive. Well, you've probably been taught in previous courses to describe directions as positive or negative. So what do I mean that there's no such thing as a positive or negative direction? I'm going to come at this from several angles. So here's the first. Remember your friend Sam, who you were texting with in an early video lecture. So you and Sam have known each other a long time, and here you both are as kids on a railway handcart. And I've drawn a velocity vector to show that you're going 5 meters per second east. However, you may describe that differently. One of you may say that you're going 5 meters per second forward, and the other might say you're going 5 meters per second backward. Well, this is because you may disagree on how you've defined your coordinates. One of you might use those blue coordinates, and the other might use those orange coordinates. That doesn't change the fact, though, that the velocity, no matter how you define your coordinates, is this green vector that points east. So the velocity vector, because it's determined from a displacement vector, which is coordinate independent, and a time interval, which is independent of when we define t to be 0, doesn't depend on our coordinates. No matter however, the components of the velocity can depend on the coordinates. So there's a difference between the components, which is to do with how we describe the velocity, versus the velocity itself. Let's think about the motion of the cart in the same way. Early on it was going to the right, and so its velocity vector would be like what I've drawn here. Later on it was going back to the left, and its velocity vector would look the way I've drawn it here. Now, we're working with a set of axes that look like this, and this is basically being imposed on us by the fact that we're using the motion sensor here to measure x. And so we got an average x component of velocity like so, 0.526 meters per second for this piece of the motion, and like so, negative 0.829 meters per second for this part of the motion. In general, the velocity vector, not these components, would be an x component times I plus a y component times j. Well, in both of these cases, because the velocity is parallel to the x-axis, we know that the y components are 0. And so we can just write the velocity, or at least the average velocity vector here as 0.526 meters per second, all I. And we could do the same thing here. But now we should think about what would have happened if we were using different axes. Now suppose that we orient our axes the other way around, with the x-axis pointing left. Now you might not like that much because I'm sure you're used to the x-axis pointing right, but just suppose that our motion sensor was at the other end of the track. Then it would be determining the position using that set of axes. So then we would have, during the rightward motion, a negative x component of velocity, and during the leftward motion, a positive one. So whether this component is positive or negative totally depends on our choice of axes, and there's no such thing as a positive or negative direction until you've defined your axes. And even then, all you can say is positive x direction, positive y direction. There's no single direction that's positive. We could, if we wished, work with a set of axes like this. And now, if the velocity was still this way, now our velocity would have a positive x component and a negative y component. So the part of the point here is that vectors aren't positive or negative. Their components can be positive or negative, but it's meaningless to say that a vector quantity is positive or negative. Numbers can be positive or negative, but vectors aren't numbers. Let's check your understanding. So, Rick and Morty have noticed that their spaceship is flying away. Morty, using the axes shown next to him, has measured the velocity of the spaceship to be this. Rick is using these axes, and so what velocity should Rick have measured?